Del, or nabla, is an operator used in mathematics, in particular, in vector calculus, as a vector differential operator, usually represented by the nabla symbol. When applied to a function defined on a one-dimensional domain, it denotes its standard derivative as defined in calculus. When applied to a field, del may denote the gradient of a scalar field, the divergence of a vector field, or the curl of a vector field, depending on the way it is applied. Strictly speaking, del is not a specific operator, but rather a convenient mathematical notation for those three operators. That makes many equations easier to write and remember. The del symbol can be interpreted as a vector of partial derivative operators, and its three possible meanings, gradient, divergence, and curl, can be formally viewed as the product with a scalar, dot product, and cross product, respectively, of the del operator with the field. These formal products do not necessarily commute with other operators or products. Definition. In the Cartesian coordinate system Rn with coordinates and standard basis, del is defined in terms of partial derivative operators as in three-dimensional Cartesian coordinate system R3 with coordinates and standard basis. Del is written as del can also be expressed in other coordinate systems. See for example del in cylindrical and spherical coordinates. Notational uses. Del is used as a shorthand form to simplify many long mathematical expressions. It is most commonly used to simplify expressions for the gradient, divergence, curl, directional derivative, and Laplacian. Gradient. The vector derivative of a scalar field is called the gradient, and it can be represented as it always points in the direction of greatest increase if, and it has a magnitude equal to the maximum rate of increase at the point, just like a standard derivative. In particular, if a hill is defined as a height function over a plane, the 2D projection of the gradient at a given location will be a vector in the xy plane pointing along the steepest direction. The magnitude of the gradient is the value of this steepest slope. In particular, this notation is powerful because the gradient product rule looks very similar to the 1D derivative case. However, the rules for dot products do not turn out to be simple, as illustrated by divergence. The divergence of a vector field is a scalar function that can be represented as the divergence is roughly a measure of a vector field increase in the direction it points, but more accurately, it is a measure of that field's tendency to converge toward or repel from a point. The power of the del notation is shown by the following product rule. The formula for the vector product is slightly less intuitive because this product is not commutative. Curl. The curl of a vector field is a vector function that can be represented as the curl at a point is proportional to the on-axis torque to which a tiny pinwheel would be subjected if it were centered at that point. The vector products operation can be visualized as a pseudo-determinant. Again, the power of the notation is shown by the product rule. Unfortunately, the rule for the vector product does not turn out to be simple. Directional derivative. The directional derivative of a scalar field in the direction is defined as this gives the rate of change of a field in the direction of. In operator notation, the element in parentheses can be considered a single coherent unit. Fluid dynamics uses this convention extensively, terming it the convective derivative, the moving derivative of the fluid. Note that as a scalar, when operating on a vector it must be distributed to each component. Laplacian. The Laplace operator is a scalar operator that can be applied to either vector or scalar fields. For Cartesian coordinate systems it is defined as, and the definition for more general coordinate systems is given in vector Laplacian. The Laplacian is ubiquitous throughout modern mathematical physics, appearing in Laplace's equation, Poisson's equation, the heat equation, the wave equation, and the Schrödinger equation, to name a few. Tensor derivative. Del can also be applied to a vector field with the result being a tensor. The tensor derivative of a vector field is a 9-term second-rank tensor, but can be denoted simply as, where represents the dyadic product. This quantity is equivalent to the transpose of the Jacobian matrix of the vector field with respect to space. For a small displacement, the change in the vector field is given by product rules. Second derivatives. When del operates on a scalar or vector, either a scalar or vector is returned. Because of the diversity of vector products, one application of del already gives rise to three major derivatives: the gradient, divergence, and curl. Applying these three sorts of derivatives again to each other gives five possible second derivatives. For a scalar field f or a vector field v, the use of the scalar Laplacian and vector Laplacian gives two more. These are of interest principally because they are not always unique or independent of each other. As long as the functions are well behaved, two of them are always zero. Two of them are always equal. The three remaining vector derivatives are related by the equation, and one of them can even be expressed with the tensor product, if the functions are well behaved. Precautions. Most of the above vector properties rely only on symbol rearrangement, and must necessarily hold if the del symbol is replaced by any other vector. This is part of the value to be gained in notationally representing this operator as a vector. Though one can often replace del with a vector and obtain a vector identity, making those identities mnemonic. The reverse is not necessarily reliable, because del does not commute in general. A counterexample that relies on del's failure to commute. A counterexample that relies on del's differential properties. Central to these distinctions is the fact that del is not simply a vector, it is a vector operator. Whereas a vector is an object with both a magnitude and direction, del has neither a magnitude nor a direction until it operates on a function. For that reason, identities involving del must be derived with care, using both vector identities and differentiation identities such as the product rule.